So I hear from Ryan that you can hear me and see my screen. How about you, Joshua? Can you see my screen all right? Can you hear me? Can you hear me, Joshua? Okay, so I've got the screen. I've got the chat on my screen, and so I can see you say something. So if for some reason some of the system goes out, just try to type it in chat, and if I notice it, then I'll deal with it. If I don't notice it and keep going, you might actually have to speak something. But that being said, we can speak back and forth. So I have no problem with you just chiming in and tapping your mic and just asking a question. All right, so that's not a big deal. It's not. We're not such a large meeting that we can't just talk back and forth. But just some things to make things run smoothly. All right, so I'm recording this, and this will be posted in Canvas in the online instruction module under like the live tutoring and help sections or something like that as soon as I get it done. The goal of these meetings is first and foremost is to answer any questions you have of the material you're working on. Because by and large, you're going to be learning it on your own as you go through the example problems, as you go through the text. All right. So I want to deal with questions that you might have first of all, and so in order to make our time here efficient, you're going to want to have those prepared, written down, and we'll be much better at getting started. We'll have everything ready to roll going forward. So anyway, this is, I really envision this mostly as a tutoring session, helping you work through the problems. Now, once you get done with problems, once we get done with your questions, then I'll work a few examples and things like that. That being said, I've also worked examples already. Did you guys find those examples? Just give me a yes in the chat. Did you guys see those worked examples in Canvas already? So that's going to be how. Yeah. So look in there, and that's going to be how. That's basically a lecture, right? So I'm going to work 3 or 4 examples, which is typically what we did in our normal classes. And hopefully that'll get you rolling on things, and then you can start working on the homework. All right. So that's where we're at. If you guys have questions, just tap your mic and just ask them if you've got them anytime. I'm just going to jump in and do a problem, and we'll to demonstrate the stuff you're learning in this section. So this section is called applied optimization. So basically what it is we've already done this. We've already found, basically what we're doing here is we're finding minimums and maximums. And we've already done that. So you remember how to find minimums and maximums. You just finding the derivative and finding the critical points, right? And that's where your minimums and maximums are. So we've already laid the groundwork for doing this. The only difference here is that the minimums and maximums that we find will be from functions that are generated by story problems. All right. So story problems will form what we're working on here, and we're trying to minimize and maximize those. And I've given some examples of those in the book, or in Canvas in the example sections. Maybe I need to do this. So let's just look at some examples here. And this is going to be what it's going to look like. So here's what we're going to do. We're going to take we want to take a rectangular box. And again, feel free, we're small, that you guys can jump in and ask questions, can actually speak them through your mic. We're going to take a rectangular box with a square base. Okay, so the base has to be square. And we want it to have a volume of 216 cubic inches. All right. So the question is, what should the dimensions, what dimensions with this subject to this constraint give the minimum surface area? Okay. So these problems are kind of interesting because just think about it this way: we've got to have a box, and it's got to have a square base. That's the only big thing, and it's got to hold 216 cubic inches. But there are ways we can do that. There are a number of ways we can do that. We could make it so that it's just a small little short box, right? Or we can make our square base such that it's very, very tall, right? So we can make all kinds of different boxes that have this kind of volume, but they're going to be different shapes. The question is, we need the minimum surface area, and that's an important question because surface area just basically translates into how much material does it require to build the box, right? And so if you're building out of cardboard, obviously you want to use as little cardboard. You want to minimize the amount of cardboard as much as you can, so that it doesn't cost you extra money. Okay, so that's kind of what we're asking: is we want to build this box that holds a certain amount, but we want to do it so that we have minimum surface area. All right. So when you look at these problems, you're going to draw a picture, and you need to understand. This is a horrible picture, but you need to understand that you can make a variety of different kinds of boxes that meet the requirement, but they will have different surface areas. And then what we do is once we've drawn the picture and maybe labeled it, let's come up with maybe a more user-friendly box. So here's our box. Okay. And we don't know what its dimensions are. We know the base is square, so we're going to have an X and an X. And then we don't know what the height is going to be. Okay. Now, here's where we run into our first challenge with these problems, and that is you don't want to have two variables. You don't want to have X's and Y's. You just want to have X's. All right? So we've got to get rid of that Y. We've got to write that Y in terms of X. And usually to do that, we can use this little constraint they've given us. So we know the volume of this box is base, or length, times width, times height, right? X, X, Y. And that's supposed to equal 216. What that lets us do is say, oh, Y's got to equal 216 divided by X squared. So instead of Y, we'll have 216 over X squared. So those are our dimensions of the box. X, X, 216 over X squared. All right? Now, what you're always going to do is after you kind of draw your picture and make your labels, you want to look and see what the question is. They want the minimum surface area. So what that tells you is you need to find an equation, a formula for surface area. All right? For surface area. And that's what you're going to minimize. So based on our little box here, surface area, right? Let's see, we've got, I don't think, it's got an open top. So we don't have to worry about the top. But we do need to worry about the sides and the base. So the surface area is going to be the area of the base, which is just X squared. That's just the area of the base. The area of one side is X times Y, or X times 216 over X squared. That's one side, and we have four of them. So if I clean that up just a little bit, 4 times 216 is what? 864 over X with a kid. So there's our formula for surface area of this open topped box. Just give me a plus. Give me a plus in the chat if that's all making sense. We're really trying to keep things simple and streamlined here. Joshua's got a plus. Ryan's got a plus. Okay, perfect. All right, so once you have that, once you have the formula for surface area, then you're just going to find the minimums and maximums, just like always, right? So at this point, we do what we did 3 sections ago, and we just say, okay, well, we're going to take the derivative. Is 2x minus 864 over x squared. And there's the derivative. We want to know when does that equal 0, so we have a little equation to solve, right? And so to solve this equation, I'm going to multiply both sides by x squared. That has the effect of eliminating this fraction. And that gives me a 2x cubed minus 864 equals 0. Fairly simple equation to solve. Right, we're going to get x cubed equals, when I move the 864 over and divide by 2, it's 432. That's what x cubed is. And so now I need to take the cube root. Anybody got what's the cube root of 432? I'm not going to ask you for that. I'm just going to find it. So it's about 7.6. And so that's what x needs to be in order for us to get the minimum surface area. And so our dimensions would be, let's see, so if that's x, then y is 216 over that squared. So that's a 3.8. And so our dimensions, so 7.6 times by 7.6 by 3.8. So let's double check. Those should be dimensions that give us a box with a volume of 216. So I'm just going to multiply those out. 7.6 squared times 3.8. And yeah, I've done a lot of rounding, so we're not exactly at 216. That says 219, but I rounded like crazy. But that's going to work, and that will give us that box that has that volume and has that specific surface area. And so there it is. So those are the dimensions. So you can see this kind of problem is exactly what we've been doing, right? It's the same kind of thing we've been doing. In terms of finding the minimum dimensions, right? Finding the critical point. So all we do is we need to build the equation first from the story problem, and then we find the extreme. Okay, so that's what's going to happen. And so you see a variety of types of equations in here of situations that become kind of interesting. Do you guys have any questions on that? Give me a plus if that makes sense, or just ask a question if you've got them.
All right, so I got a quick question for you on that. Would you just go through like what the basic process is, what basic steps you go through to get to the end thing? Just to review it.
To get to what?
To get to the end, so kind of like, this is your first step, this is your second step. Kind of a basic overview of.
Yeah. So let me point you to. Wait 1 second. I'm gonna mute and step away for 1 second. Give me 1 second. All right, I'm back. Let's see, I'm back. Okay. So as far as steps go, I would just point you to page. Now, these are story problems, right? So, with story problems, there are a million different flavors of story problems. So there's never one way to do it. They're just some guidelines. And we'll go through another problem and try to illustrate those guidelines. But if you want to maybe think about some steps, look on page 441 of the book. All right? So it kind of goes through this process. And what we'll do is we'll do another problem, and we'll kind of talk about those steps as we go so you can kind of see what they mean. All right? So we'll see if that helps us a little bit. Okay. All right. Let's try to do one of these. Okay, so let's look at this here. All right, so here's a problem, just to show you again the variety. So let's say you can run your running speed. And again, I'm assuming you're still seeing my screen here. Your running speed is 6 miles per hour. Your swimming speed is 3 miles an hour. And you're sitting on the shore, all right, 4 miles east of an island that is 1 mile north of the shoreline. All right. So let's see what we got here. Here's you. Now we're east of an island. So here's you. Here's the island. All right. Oh, there's you. There's the little island. All right. And you know the dimensions are this is 4 miles. And this is 1 mile. Right? And so all of this is water. And you're on this nice, straight, perpendicular shore. Okay? And you want to get to the island. Okay? So the question is, how far should you run west to minimize the time to reach the island? Let me see if I've got this. How far should you run west to minimize the time needed to reach the island? I'm quite certain. Running west. Oh, I got it. I see. I got the shore the wrong way. You're still in the same place. I was freaking out there. Let's try that again. There you are. The shore is here. This is the shore. Now. Okay. So no water. Got beaches. Beach umbrellas here. Right? Those chairs. But we all wish we were on a beach somewhere right now. But the question is, we're going to have to get to the island, we're going to have to do some swimming. We could swim the entire way, right? We could swim the entire way. We could go, straight from where we're at and across. But we're slower at swimming than running. We could run all the way and then swim this little bit. But the question is, what's the right combination? Because obviously if you run straight across, straight down until you're here and then over, you've really taken, you've covered the maximum distance. So maybe that's not the fastest you can do. So the question is, at some point, we're going to run up to some point, right? So we're going to run up to some point, and we're going to call that distance x, okay? And then we're going to swim the rest of the way, all right? And so let's label this. X is easy. We might say that we're swimming y, but remember we've talked about the fact that we don't want variables in there that are that more than just x's. We don't want to introduce new variables. So here's what we're going to do. We know that this distance is x that I've got labeled. This distance of this little triangle right here, I'll color it in. So of our little triangle, and I guess I'm going to have to, unfortunately, erase the beach chair. This distance is 4 minus x, right? It's the rest of the 4 miles after we take the x away. So then this distance being a right triangle, that yellow being a right triangle, we can use Pythagorean's theorem to come up with that distance that we're going to have to swim, the blue side. And so, of course, that's going to be, we'll just call it d, and it's the square root of 1 squared plus 4 minus x squared. That's the Pythagorean theorem that gets us that distance. And the nice thing is, that is now just in terms of x. All right? So let me just clean this up. This is going to be 1, since we're going to need this in our calculations. Let's see. It's 1 plus 16 minus 8x plus x squared, or it is x squared minus 8x plus 17. So that's the distance that we're going to swim. So we're going to run x, swim this little square root distance. And now we've got our picture labeled, all right? So as we look back at 441, that little process, we've introduced all the variables and draw a picture of and label everything. We've just kind of done step 1. Now we're to step 2, which says determine what is the quantity to be minimized. So the question, I didn't write this down in, is how far should you run west to minimize the time needed to get to the island? So that's phase 2 is recognize what it is we're trying to minimize. And then phase 3 is let's write a formula for the time to get to the island. Okay? We're trying to minimize that. So now we're going to use the classic distance equals rate times time formula, right? Which, of course, means also that time is equal to distance divided by rate. So the time it takes us to get to the island is going to be the time that we walk, right? So the time that we walk or run, I should say, plus the time that we swim, right? So the time that we run is going to be the distance we run, which is x, divided by the rate that we run, which is 6. The time that we swim is going to be the distance that we swim, which is x squared minus 18 plus 17, or minus 8x plus 17, over the rate that we swim, 1/3, or 3. And that is the total time. Okay? So just give me a plus if that makes sense, or chime in with a question if you have it. Okay, that's good. All right, so that was step 3, which was to write a formula that was to be minimized, right? And you can see that we've used about a dozen different things. We used Pythagorean theorem, we used this stuff, so that's kind of what's happening here. All right, so right now we're done. We're now stepping back into familiar territory, which is to say we now know how to minimize this equation, or to optimize it, to find the extrema, find the derivative, and find the critical points, right? So, of course, the derivative here is 1/6, right? Because x over 6, remember x over 6 is the same as 1/6 x. So the derivative of that piece is just 1/6 plus, now the 1/3 hangs out, and I'm going to take the derivative of the square root, which is 1/2 x squared minus 8x plus 17 to the minus 1/2, and then times the derivative of the inside, which is 2x minus 8. So chain rule. So 1/6 plus 1/6. We'll have a 2x minus 8 on top. We'll have a square root or a 6 square root of x squared minus 8x plus 17 at the bottom. And that's our derivative, and we want to figure out where that equals to. Okay. So now we've got a little bit of algebra. So I'm just going to kind of cruise through some of this algebra here, and you guys can chime in with questions if you want. But so let's multiply everything by 6 square root of x squared minus 8x plus 17. This just gets rid of all of the fractions. And so it's going to look like this. It'll leave me a 1 times the square root of x squared plus 8x plus 17 plus 2x minus 8 equals 0, right? Because the whole fraction disappears. Multiplication by 0 on the right side is 0. And so that's our equation we want to solve. So, we dig back into our algebra toolkit. If I want to solve an equation that involves a radical, I have to first isolate the radical, so get the radical by itself, and then eliminate it. Got to get rid of the radical. So the good news is that's just this. Right? That left side just becomes that. The right side is going to become 4x squared minus 32x plus 64. Okay, just sorting that out. And right now we're going to combine our like terms. Let's move everything to the right. So let's move everything over this way. And so that's going to give us a 3x squared. We'll subtract an 8x to get a minus 40x. And we'll subtract a 17 to get a minus 47 equals 0. Now that does not look factorable to me. Right? Does not look like you can factor that. Let's see if I can do this. There we go.
Should the 47 be positive since you subtracted 17 from 64?
Yes, you're right. Thank you. Okay, so we're going to need a new sheet. Yeah, so positive 47. Okay, so that's it, right? There's a quadratic, so we know we can solve it. We can throw it into the quadratic. We might be able to factor it, but it looks to me like it's going to be easier just to do this. Right? So x is equal to 40 plus or minus. Let me grab my calculator real quick. That is 1036 over 6. Are we lucky? Are we lucky to get a nice? No, we're not. So this is about 40 plus or minus 32.19 over 6. And so you can see the reason I write that out is because we want decimals. We need decimals. We need answers. So if I do 40 plus that, I'm going to get about 12. Okay? And then if I do 40 minus that, I'm going to get about 2. Okay? So now here's the deal. Remember what X represents. If you go back to the previous screen, right? X represents the distance that we are running down a 4-mile shoreline. Well, it doesn't make any sense for us to run 12 miles down a 4-mile shoreline. So we throw that one away. Boom. There's our answer. We're going to run 2.6 miles down. We're going to jump in the water and swim to the island. And that will minimize our time. And that's a real interesting problem just because, it shows you this, that, I mean, it maybe feels like a weird question, but there are times when we minimize and maximize these kinds of things all the time. And this gives us the ability to do that. So, all right. Why don't you, rather than just plus or minus, tap your mic and tell me what your thoughts are. If these two problems make sense to you, if you got further questions, I'd kind of like to hear a voice.
Makes sense to me. So far.
All right, Ryan.
Will rate always be velocity?
Yes. In these kinds of problems, rate is just velocity. So, all right, we are about out of time here. That gives you a couple more examples of what we're doing in this section. I'll get that homework posted for you here in a moment. And then this I'm gonna, if things work right, I'm still toying with it. If things work right, this I'll get posted in the Canvas course as well. This recording of this session. All right. And then we'll be back here on, I guess, Monday. We're just doing this Mondays and Wednesdays. And again, do you guys have any questions on how you're going to learn this material as you go throughout the rest of the semester? Hopefully you've seen what in the Canvas course, and that answers a lot of questions.
What's the best way to get a hold of you if we do have other questions during the week?
Yeah, definitely send it to me in Canvas. That's really the only way to do it, and then I can reply to it easy enough. All right. Okay, guys. Good luck. And again, send me messages in Canvas. This represents a little bit different than we've been doing, but there's no reason we can't make this work. We've got the technology, and heck, heaven knows that we don't have anything else to do, right? So we might as well spend our time doing calculus. Let me know if you've got questions, and we'll go from there. So we'll see you Monday, same time.